Okay, welcome to lecture here. Okay, so last time we really finished up talking about nomenclature, which was basically the end of chapter three, the last little section in chapter three. So just a reminder that we are going to have a quiz today. We'll lecture first and then take the quiz at the start of lab. And I think how we'll do it. Um, so last time we did talk about nomenclature, which pretty much everything in terms of naming. We talked about type 1, type 2 compounds, which are ionic compounds. And whenever you have a type 1 or type 2 compound, that's a metal and a non-metal together. It's always the metal that is the most important person there in that compound. And it depends on really where the metal is on the periodic table. So if the metal is in group 1, 2, or 3, or if it's zinc, cadmium, or silver, they have fixed charges, which means we don't need any Roman numerals or anything like that. So as we talked about last time, that's the whole name of the metal, IDE on the non-metal, last part of its name. If you have a metal and a non-metal and that metal is a transition metal or just to the right of the transition metals, those guys have variable type charges. So we do need to use Roman numerals when we name those type. And the Roman numeral, as we talked about last time, is the actual positive charge that there is on the metal. Um, so kind of the same type of way of naming. Whole name of the metal, Roman numeral to indicate the charge, IDE for our non-metal on the back end of its name. Then we also talked about polyatomic ions, which again are groups of non-metals that are together that have a certain charge, a certain name. You just sort of has to kind of memorize those guys. Again, usually either end in ate or ite. The ate is usually the ones that have the most oxygen in like a group of 2 or 4. Ite has the least oxygens in a group of 2 or 4. And if you happen to have a group of 4, we put other things. So the one with the most oxygens in a group of 4 starts with per and ends with ate. The one with the least oxygens in a group of 4 starts with hypo and ends with ite. And again, if we put like H plus in front of something, then we call it hydrogen carbonate or something of that nature. For the most part, most of the polyatomic ions are negatively charged, which means they typically are hooked up with a metal, which means you follow kind of the type 1 or type 1 or type 2 rules with it, which means, again, it's the metal that's really the most important thing there, whether or not you need a Roman numeral. We also talked about type 3 guys, which are two nonmetals together. So that's a covalently bonded guy, molecular compound. That is the one that we use prefixes for. Again, the only kind of rules on that one is no mono on the first name, but you can use mono on the second. Um, Also, if you have an A and an O that kind of backs up to each other from the prefix and the first letter of the next name, we drop the A. Also, two O's, we drop the O. And whole name of the first element with the appropriate prefix. IDE on the second element with the appropriate prefix. And again, those are pretty easy since there's nothing really to balance, no charges to figure out or anything like that. I just pretty much need to pick the right prefix. We finished up, I think, talking about naming acids. A reminder that when we name acids, it's really all about oxygen. So if there is no oxygen in an acid, you will start with hydro something ic acid. The middle part there is the negative anion. A cation for all acids are H pluses. So H plus is always a cation. Then if we do have oxygen in our acid, it's sometimes referred to as an oxyacid, and it will typically have a polyatomic ion that's present. And if that polyatomic ion ends in 8, the acid will be something ic acid. And again, that first part of the name would be the anion or the negative part. And if the polyatomic ion ends in ite, then it is something OUS acid. Again, the first part of the name being the negative anion that's present. I think that was all the naming we talked about. Any questions on naming or any of that stuff before we kind of continue on here to the next topic? Okay. So we're then going to roll, I think, 5-ish, 6-ish, kind of a mixture, both of these chapters, I think. Basically, we're going to talk first off about balancing chemical equations, how to, again, properly balance chemical equations. Then we're going to talk about different types of chemical reactions and ways to classify chemical reactions, including double displacement reactions, redox reactions, and some different classifications underneath all of those types of big umbrella classifications. But we'll start here with the basics of, again, chemical equations and balancing chemical equations. So when we do have a process that involves a chemical change, that usually involves a chemical reaction that takes place. The way that we sort of represent a chemical reaction taking place is obviously with a chemical equation. So a chemical equation is really the formulas that are involved for the species, obviously the arrow that's happening. And when we look at a chemical reaction, we have basically two main parts of it. On the left-hand side of the arrow over here is our reactants. Our reactants are our starting material in a chemical reaction. On the right-hand side of the arrow, we have our products, which are obviously the substances that are formed as a result of a chemical reaction. A couple other things that we commonly do see in sort of chemical equations, in addition to sort of the formulas, we oftentimes will see symbols that are written, obviously next to each of these guys. And these symbols usually will indicate the state at which these species are in, S being solid, L being liquid, G being gas, and AQ being the aqueous state, and that's usually some type of water environment. Now, very often people sometimes are maybe a little confused about, again, the difference between something that is L and something that is AQ. And the difference is if you are something that is L or a pure liquid, it is basically just one substance that's present. So for example, if we have just water by itself, that is a pure liquid. If we take water and mix it together with something like sodium chloride, when those guys come together, the sodium chloride will dissolve and make a sodium chloride solution, which gets the aqueous symbol. So aqueous usually means that you kind of took something, kind of dissolved it in a solvent, maybe something like water, and you made a solution. A liquid is a pure liquid, which typically means that, there's nothing else there other than whatever that liquid may be. So again, that's the major difference between, say, something that's a liquid and something that is aqueous. Other common things that we do see in the equation is we see a lot of things sometimes written on top of the arrow. For example, we may see a little delta symbol that usually means heat. You may actually see something like platinum written. You may even see something like H plus written, which means an acid. So a lot of times up on top of the arrow, we put things that are catalysts. And catalysts are things that are added to a chemical reaction. They're not a reactant. They're not a product. They're there simply to make the reaction usually occur faster. So usually we'll speed up a chemical reaction. But again, a catalyst is not a reactant. It's not a product. And it actually does not get used up. It actually is just there to simply sort of facilitate that reaction occurring faster. Again, it may just be allowing things to come together in a more efficient manner, but it really is not part of the overall reaction that is taking place. Sometimes we'll also see, for example, water slapped up there on top of the arrow. And usually that's for a process where we are dissolving something in water. So that's, again, another thing that's sometimes written up on top of the arrow. We don't necessarily always use a sort of chemical equation to represent always a chemical change. We can have something like H2O, say liquid, to H2O gas. Obviously, this is still H2O on both sides. This is just a phase change that's occurring. So again, sometimes we can use a chemical reaction to sort of indicate what's happening in terms of the phases of the substances. When we look at a chemical reaction, there's a lot of important sort of relationships that we could get from it. And some of these will come into play a little bit later on when we talk again about stoichiometry and all that good fun stuff everybody loves. But we could look at the coefficients in sort of a balanced equation and basically come up with some relationships. We could say, for example, that there are two atoms of magnesium here are reacting with one molecule of O2 to form two formula units of magnesium oxide. Formula units is sometimes used for ionic compounds. Just like when we talked about, for example, atomic mass earlier, for ionic compounds, sometimes people will refer to it as formula mass because they're technically not molecules and stuff like that together. They're technically ions together. They're not sharing electrons. So formula units are sometimes used for ionic compounds. And again, sometimes formula mass instead of molar mass is sometimes used for ionic compounds for those purposes. Really, the relationship that we use a lot, and that you probably have used a lot in past as well, is this relationship here. This is really the mole to mole relationship that you could get from a balanced equation. Also just comes from the coefficients. We could say for every 2 moles of magnesium, it reacts with 1 mole of O2, gives us 2 moles of magnesium oxide. Again, that mole to mole relationship, a very useful one, and really the relationship that we use in stoichiometry. We could also have this relationship here. We have 48.6 grams of magnesium plus 32 grams of oxygen gives us 80.6 grams of magnesium oxide. That's that conservation of mass, and really the whole point behind balancing equations. When we start, we never lose any elements in a chemical reaction. All the elements are just basically rearranged and recombined as maybe new species. And that means that in this case, for example, here, we start with 2 magnesiums. Each magnesium is about 24 grams. We have 2 oxygens on the left. Each one's about 16. And on the right-hand side, we end up also with 2 magnesiums and 2 oxygens, which each have the same mass. So we have that kind of conservation of mass there. And really the whole point behind balancing is that idea that we don't lose any elements along the way. One relationship we can't do is the gram to gram relationship. So that relationship doesn't work by using the coefficients or anything like that. So that is definitely not one that works. And again, we will definitely see the mole to mole relationship in just a bit. So let's talk about balancing equations. And obviously when we have an equation, we always want to make sure that it is balanced. And a couple important things about balancing an equation. First off, obviously, the whole goal is to get the same number of elements on both sides. When we do that, the only thing that we could change are the coefficients that come in front. So we could only change those numbers that come in front of formulas and equation. We never like put a number between things. So if we have like H2O and we're trying to balance it, we never put like a big 4 in the middle or anything weird like that. In addition, basically most people do sort of a trial by error. They kind of put some coefficients on the left, coefficients on the right, until everything sort of is balanced. Now, there's really 2 main things that has to happen when you properly balance an equation. First off, when it's all said and done, all the coefficients need to be whole numbers. So all the coefficients need to be whole numbers. And they need to be the simplest set of whole numbers. So really what I mean by that, for example, is let's just say we had a made up equation here. So let's just say we took 4a plus 2b gave us 8c, and we'll just say that this equation is balanced. Now, if this equation is balanced and maybe we use all these coefficients here to get us to balance this equation, when we look at the coefficients, we actually can reduce everybody here down by 2. And you should do that. So you would want to reduce everybody down by 2 to get the properly balanced equation of like 2a plus b gives you 4c. So it's really important. And this sometimes happens because honestly, everybody's a little bit different. Some people can see kind of the bigger numbers in their head and like balance everything. Some people can't and stuff like that. So it is potentially possible that you could balance the equation with larger numbers. But if you can reduce everybody down by a common number and still maintain the whole numbers for everybody, then you should do that. So my approach to balancing equations is, and it's a good idea to do, I think, is to make kind of like a table. It's usually sometimes very helpful. First off, what you want to do is you want to make sure, first off, before you balance the equation, that if you happen to be given everything in words, that you start out with the proper formulas. So very often what happens with sometimes with people is they try to balance the equation and write the chemical formulas at the same time. And usually what they end up doing is getting the wrong formula down, and they sit there all day trying to balance something that will never balance because you're not starting with the right formula. So what you should always do in that situation is make sure right formula, forget about the balancing, and then you should go back and balance everything with the coefficients. And that especially happens a lot when you're given like the reactant side of an equation and you need to predict products on the other side. People oftentimes always want to kind of balance and all that kind of stuff and write the formulas. So always want to make sure you get the right formulas down. Then it's sometimes a good idea to lay up a little table of what you got going on. Here we got carbon, hydrogen, and oxygen happening. And on the left-hand side, I got 2 carbons. On the right-hand side, I got 1 carbon. On the left-hand side, I got 6 hydrogens. Right-hand side, I got 2 hydrogens. Left-hand side, 2 oxygens. And the right-hand side, 2 oxygens there, plus 1 more there, gives me 3 oxygens. So in this particular case, not much happening in terms of things being balanced. So we might as well start with what might be the easiest to balance, and that probably would be the carbon. So we probably would want to put a 2 in front of the carbon on the right-hand side. Again, remember that when we balance it, it is only the coefficients. So we're going to put a 2 there. When we do that, that gives us now 2 carbons on the right, gives us still 2 hydrogens on the right. And for our oxygens now, we have 4 in the first guy and 1 more in the second guy, now gives us 5. So at this point, we have now successfully balanced the carbon, but everything else is still not so much balance there. So we might as well start with what's the next easiest, and that for me would probably be hydrogen at this point. So we would put a 3, again, coefficient in front, nothing in the middle or change any of the subscripts. When we do that, we still have 2 carbons. We now have 3 times 2, which is 6 hydrogens. And our oxygens now have gotten to 4 in the first one and 3 more in the second one. That's a lot of math, but I'm going to go with 7 at this point. And at this point there, we now have our carbons balanced. We have our hydrogens balanced. We do not have our oxygens balanced at this point. Any questions so far on that? At this point, we want to fix the oxygen. We clearly don't want to probably do too much on this side since we've already put numbers in there. So if we went back and started changing things, you'll never move forward. So we really do have to focus on the oxygen on this side. So we basically need to turn our 2 into a 7. So obviously to do that, one way that you could do that is to do something like 7 over 2. So if you use 7 over 2 and you multiply it by 2, that gives you 7, which is what we're looking for. So if I go 7 over 2 in front of the oxygen, that gives me 2 carbons, gives me 6 hydrogens, and 7 over 2 times 2 gives me 7 oxygens. Now this equation is balanced, but it is problematic because my rule over here is They all need to be whole numbers. So in this particular case, you absolutely can use a fraction to balance it. But if you use the fraction, you then need to get rid of it to have the properly balanced equation. So to get rid of a fraction, we want to multiply everything by the guy on the bottom. They think they still call that the denominator, I hope. So we're going to multiply everything here by 2. And that's going to give us 2C2H6. Or 7/2 times 2 will give us 7O2. On the other side, multiplying the 2 across gives us 4CO2. And lastly, 6H2O. So if I didn't screw this up here, we should still be balanced. So I have 4 carbons on the left, 4 on the right. We have 12 hydrogens on the left, 12 on the right. We have 14 oxygens on the left, 8 oxygens in the CO2, and 6 more is 12. All right, what we got there? 8 and 6 is a lot of math. 14, I could do that math, I think. So we are balanced at this point there. So this is a very good example that, you know, sometimes the best approach is to maybe use a fraction, which you absolutely can do, but you do need to clear the fraction in order to have a properly balanced equation. Now, some people ask, like, how do I know what fraction to use? It's a pretty simple formula. The top number is the number you need. So if you remember, we needed 7, so up on top went 7. The bottom number should match the number that's a subscript over here. So if you look, the 2 matches. So that's a good way to just easily figure out what you need. Top number, what you need, bottom number should match, and you should have the right fraction that you need there. Question on any of those steps there? All right. In case you wanted the step-by-step, you could watch this later, I suppose. There we go. That was a long way to get there. All right, there we go. All right, so why don't you give this one a go, see what you come up with, balance it up. Okay, so let's take a look here and see. So again, if it's helpful, make a table. A lot of people do find it helpful to kind of do it that way. So nitrogen, oxygen, hydrogen. Again, we got one nitrogen on the left, two on the right. So we got one oxygen on the left and one on the right, and two hydrogens on the left and two on the right. So again, table just kind of helps you maybe figure out where's a good place to start. We can see everybody's balanced here except for nitrogen. So that seems like the good place to start. So we'll put a 2 there. When we put a 2 there, that gives us two nitrogens, gives us now two oxygens and two hydrogens. And this usually happens as you balance one thing, you kind of screw up something else. So we will then probably balance our oxygen, which is probably the easy thing here, and put a 2 in front of it. On the right hand side, we now have two nitrogens, two oxygens, and 2 times 2 is 4 hydrogens. So we fixed our oxygens, messed up our hydrogen. So we then could go back to the other side and also put a 2 there. And that I think should do it for us. Two nitrogens, two oxygens, and 4 hydrogens. Any questions on that particular one there? So again, at no time do we want to put anything in between formulas, change any of the subscripts, because obviously that does change what it is. Yeah. All right. All right, give that one a go, see what you come up with. Okay, so let's take a look. We got 3 carbons on the left, 1 on the right, and 8 hydrogens on the left, 2 on the right. Oxygens, we got 2 on the left. And again, we have 3 oxygens going on here. So again, probably the easiest thing to start with would be our carbon. So we could lay up a 3 there, and that's going to give us 3 carbons, 2 hydrogens. Oxygens, we got 6 in the first one, and one more makes 7. Now, probably the next easiest thing would be to balance our hydrogens. We got 8 on the left and 2 on the right. So a 4 there should probably do it. We're going to do a 3 for the carbon, hydrogen now 8, and oxygen, we are now up to 6 in the CO2 and 4 more. That seems like 10. And lastly, we could go back the other way there and pop a 5 in there. And that should give us 3, 8, and 5 times 2 would be 10. So all balanced at that point. Any questions on that one? Okay. Give this one a go here. Okay, so here, if we have everything in words, like we were saying before, you do want to make sure you just get the right formulas down first. So diboron trioxide, that's a couple of nonmetals. So that's going to be B2O3. Reacts with water, which hopefully we know is H2O, to form our boric acid here. So not worrying about any balancing or anything like that. We just want to make sure get all the right formulas. Now we can worry about the balancing part of it. And we got boron, oxygen, hydrogen. So we got 2 on the left, 1 on the right, and 3 on the left, plus 1 more makes 4. And on the right hand side there, we do have 3. We need to distribute that in to both of these guys here. On the left-hand side, we got 2 hydrogens. Distributing that guy in gives us 3. Not a lot to work with here, so might as well start with our boron and fix that, put a 2. When we do that, that gives us 2. Also need to distribute the 2 along with the 3 to everybody else. That gives us 6 of the oxygen and 6 of the hydrogen there. At this point, we could pretty much fix the hydrogen by putting a 3. That gives us 2 boron and oxygen, 3 and 3. So that fixes our oxygen and also fixes our hydrogen in that particular point. Question on that one there. Okay. And one more maybe. Get our ghosts come up with. Okay, let's take a look here. So reactant product. Got some nitrogen, some hydrogen, some oxygen. We got one nitrogen on the left, one on the right. Got 3 hydrogens on the left, 2 on the right, and 2 oxygens on the left, and 2 oxygens on the right there. Everything's looking good except for our hydrogens. So in this particular case, we probably want to fix it by going with 6. So to get our hydrogens on the left to 6, we need a 2. Get our hydrogens on the right to 6, we need a 3 squeezed in there. That's going to give us 2 nitrogen. We got 6 hydrogen and 2 more oxygens. On the right-hand side, 1 nitrogen, 6 hydrogens, and a lot of oxygens there. 4, it looks like. So fix the hydrogen and pretty much screwed up everything else there. So we might as well continue to fix some things. Let's go with the nitrogen. So we're going to fix that by putting a 2 on the right-hand side. That's going to give us 2 nitrogens. That will give us 6 hydrogens. And my oxygens are now up to 2 in the first one and 3 in the second one. That gives me 5 at this point. So again, we're at the point where clearly we don't want to play with any of those coefficients again. And this commonly happens, like we saw earlier, where you have kind of the element by itself and that element in a couple of other places. So perhaps a good course of action here would be to try to balance it using a fraction. Again, up on top would go the number you need, which is 5. Up on the bottom there would go the same number that's there, which would be 2. And if we do 5 over 2, that gives us 2 nitrogens, 6 hydrogens, and 5/2 times 2 is 5 for our oxygens. Again, you cannot leave it like this, so you do need to clear that fraction by multiplying everybody by 2. And that will give me 4NH3 plus 5O2 gives me 4NO plus 6H2O. And again, if I didn't screw anything up there, should hopefully still be balanced. That is 4 and 4. Got 12 hydrogens going on both sides and 10 oxygens on both sides. So we are balanced there. Any questions on that particular one? So again, if you find yourself not able to balance something, think about a fraction may be very helpful to kind of do that as well. Any questions on that? All right, let's just try 2 more and then we'll call it a night, I think. All right, so why don't you balance this one? Let's go with FeSO4 plus Na3PO4 goes to Na2SO4 and Fe3PO4 2. And why don't you do this one as well? Let's go with CaNO3 2 plus Al2SO4 gives us CaSO4 and AlNO3 3. All right, so why don't you give those guys a go, see what you come up with. Okay, so let's take a look at these. So now when you have something like this, you definitely can go about it the same way that we've been doing, sort of element by element. But if you look at these equations, you do see a lot of those polyatomic ions in it. So for example, there's sulfate and sulfate. There's also phosphate there and phosphate. And when you do have these polyatomic ions, sometimes it's easier to kind of keep them together when you're balancing an equation and sort of balance the polyatomic ions as like units. So for example, if we take that approach, I see I have one sulfate on the left, one on the right, so that's good. I have one phosphate on the left, but I have two on the right. So I could very easily fix that by putting a 2 in front of the phosphate. That gives me two phosphates, but that now changes the sodium to 6, which is probably the next place I would want to go to. So I would go over to the sodium and go from the 2 that I have and now make it into a 6. So that fixes the sodium. That now plays with the sulfate, which is 3 of them, which would tell me where I should go next. And I could put a 3 in front of the sulfate. Also gives me a 3 in front of the iron, which is actually what I need. And we would be balanced in this case. So sometimes it's a lot easier, especially if you have a number of polyatomic ions involved, to kind of keep them together and sort of balance them as whole units. And usually what will happen is kind of what just happened there. Everything will sort of fall into place at some point. You definitely could go sort of element by element, but sometimes there's a lot more, obviously, with polyatomic ions, a lot more kind of multiplying in, multiplying out with the parentheses, and, maybe a little bit more room for error. So if we sort of take that same approach on the bottom here, we have nitrate and nitrate. We got sulfate and sulfate here. So for example, if I start with the sulfate, that seems like an easy one to fix. So I got 3 on the left and 1 on the right. So I could put a 3 in front of the sulfate on the right. Also gives me a 3 for calcium, which would tell me that's probably the next place I should go to. So I would put a 3, maybe if it writes. I did write it 3 times. So I'm going to try the fourth time here and see if I can actually get it right. There we go. 3 calciums there. That now will give me 6 nitrates, which if I go back to the other side, I could put a 2 in front of the nitrate over here. That's going to give me 6 nitrates, 2 aluminums. And again, I do need 2 aluminums anyways. So everything basically falls into place. So again, sometimes it's a little bit easier just to kind of balance those guys as units rather than kind of individually. Any questions on balancing equations or anything like that? All right, well, it's Thursday. I need a nap. I think that's about it for today, don't you think? I think so. So I think what we'll do is we'll stop lecturing here. You can also get a chance to maybe stretch and all that good stuff before the quiz. Quiz will open somewhere around the start of lab, 7-ish, 7:15, somewhere in that ballpark. And you could take the quiz. Again, it's going to be on all the bonding. You will have to upload some work like the other quiz and the exam and all that kind of stuff. You can use a calculator if you need. I'm not sure if you really need one, but you could use it. There will be a periodic table that will be on there, kind of like the exam and quiz. So if you need to, you could PDF it, open it, and take a look at it. Again, you need to use the proctorial and all that kind of stuff like normal. Let's see. It's only, I think, a couple of questions or so. So you do need to show work on both of them. Make sure you read all the questions carefully, that you answer what it's asking. And obviously, you need to make sure you upload your work after you submit the quiz kind of immediately. And make sure that obviously your answers sort of match, right? So make sure all that's the right stuff. Like normal, no notes, all that kind of good stuff. Yes. No people, any of those things. Yes. Or anything like that. I say that because I had somebody, a last test or something, not in here, but in a different class. I got a bunch of emails. I'm sorry, but these people walked in while I was taking the exam. That's why I looked over. So, it's all right. But, no talking to anybody and all that kind of stuff as well. Other than that, for lab scheduled for today is study assignment D, I believe, which is about moles and grams, Avogadro's number, all that good stuff. So since we're taking the quiz kind of for some of the lab time, I will make that due on Tuesday of next week. You can turn it in whenever you like. The box will be up there, but it'll officially be due Tuesday at the end of lab next week. And again, I think it should be pretty straightforward. I believe we talked about moles, Avogadro's number, all that kind of stuff. So you don't really need to come back for lab if you have no questions. If you're all good, I'm good. Just make sure you take the quiz, obviously. And if you do have questions, I'll log back on about maybe 8:30 or so. So if you do have questions, feel free to hop in. If there's anybody there, I'll answer your questions. If not, that's cool. But if you're all good, you don't have to come back. Yeah, just make sure you take the quiz and all that. But if you do have questions, I'll pop back on about 8:30 through the lab meeting like normal. Other than that, any questions on anything going on?
What did you say was due on Tuesday again? Sorry.
On Tuesday is the study assignment D, which is what's scheduled for today in lab.
Oh, okay. Okay, thank you.
And again, that should be about moles and Avogadro's number. You'll have about the same amount of time as the first quiz, maybe about 35 minutes, which I think should probably be plenty, for it. And again, it'll cover all the bonding stuff, Lewis structures, geometry, formal charging, all that stuff, hybridization, everything that was in those couple of chapters. Other questions or anything? Okay. So if I don't see you, have a good weekend. Good luck on your quiz. And if I do see you, if you do have